Okay then, so this is a video I've been looking forward to make for a really long time. We're going to look at some of the most elementary geometry, but we're going to take a very kind of wide angle lens at the behavior that's possible. We're going to try and understand all of it. And in looking at this simple geometry, we're going to see so many ideas emerge from mathematics. We're going to see ideas like complex numbers, infinitesimals. We're going to see all sorts of groups of interest in fundamental physics. We're going to see so many amazing mathematical structures emerge from these really simple concepts. So this is a video I'm really excited about. I mean, a lot of the things I've been doing recently have been involving category theory, where we work with these kind of super high levels of abstraction, and we can see lots of mathematical objects through that kind of lens. But this is a bit different. What we're really seeing here is we're seeing all of these kind of mathematical concepts emerge naturally from a very, very simple starting point. So basically what we're going to be looking at are these 2x2 matrices. So we're going to be looking at linear algebra. So if you don't know about linear algebra, hopefully this video is going to provide you with a way to start thinking about that, because I'm going to introduce things from first principles. But if you do know about linear algebra, then hopefully you're still going to find this video remarkable, because we're really going to see all sorts of things that you wouldn't expect to come out of linear algebra when we do this sort of exhaustive exploration of the behavior of these 2x2 matrices. So basically, we want to understand what all of these different linear maps are from the plane to itself. And you might say, okay, they're all pretty simple. They're just these matrices. But it's really a remarkable thing when you think of the totality of all of these maps. And you note that really, because you have these four numbers in these matrices, like shown in yellow at the top here, I'll explain matrices later, but basically we have these four numbers that we can vary. And as you do so, you see that there's remarkable changes in the sort of qualitative behavior of the maps that you get. So actually, what we have is like a four-dimensional manifold, which we can partition up into different pieces representing different kinds of behavior. And we're going to see all of this remarkable geometry and really gain more appreciation for how cohesive the sort of mathematical universe is. So I've been debating quite a lot with myself about what's the easiest way to introduce this sort of geometry in these matrices. I imagine many of my viewers already know about matrix multiplication and things, but still I want to provide an introduction for anybody. So basically, we don't have to imagine a setup like this, but let's imagine a setup where we have this origin. So that's a special point on our plane. We can think of it as like our 0, point. And then we can imagine that we have these two different sorts of perpendicular directions. And so if we draw a vector like this, well, a vector is just going to be an arrow. We'll typically think of these arrows as emanating from the origin, but we don't have to. And then we can label this vector with these two numbers. One number is going to be telling us how far to the right we've moved. That will be x. And the other number is telling us how far up we've moved. That will be y. And so in this case, if I've drawn this properly, you can see that this vector constitutes moving 2 steps to the right and 1 step up. And so in this case, this vector here is going to be 2, 1. So we've moved 2 steps to the right and 1 step up. So x is 2 and y is 1. And there are some other kinds of ideas that we can see sort of playing here, which are going to be very important. So one of them is that what we've essentially done here at the bottom is we've added this vector 1, 0 to this vector 1, 0. And you can see that adding vectors, you can think of it geometrically just by drawing the vectors head to tail and then thinking about what the resultant movement is if you move along both of those vectors. And so we could write this sum here as 2, 0. Another way we can write it is as 2 times the vector 1, 0. And so what we're doing here is we are thinking of this number here as what we call a scalar. It just means a number, but it's a number that we're sort of scaling the vector by. So you can think of having this as a sort of shorter vector, and then we're taking this vector and we're multiplying it by 2. That means we get a vector in the same direction, but twice as long. And then you can see that if we take this vector here, this is the vector 2, 0, and then we add it to this vector here, 0, 1, then we're going to get this resulting vector. And so to add two vectors together, as I say, geometrically, we just do one vector and then the other. But algebraically, we just add the thing upstairs here to the thing upstairs here, and add the thing downstairs here to the thing downstairs here. And we get 2, 1 in this case. So that's the basic idea about how we manipulate vectors. So now let's have a look at these linear maps. Okay, so this is really the essence of what I want to talk about. So what is a linear map? Well, I'd like to start by defining it geometrically. Okay, so we have this plane and it has an origin. And so a linear map for us, we're interested in linear maps of the plane. That means we're sending every point of the plane to a point of the plane. And we're doing so in such a way that the origin is preserved and every line gets sent to a line. And if we have two lines that are parallel before we do the map, then they're going to be parallel after we do the map. Those are the sort of rules which define what a linear map is geometrically. Now, usually people think of linear maps in a more algebraic way, but I think it's nice to start with a sort of geometric intuition for things. So one of the key observations then about these linear maps is that they're going to send parallelograms to parallelograms. So it turns out that using this idea, we can really gain a great deal of geometric intuition for how these sort of linear maps are working. So what do I mean? Well, a parallelogram is a shape with four sides where the opposite sides are parallel. And the thing is that we can use parallelograms to describe where points are in the original coordinate system. And then after we apply our linear map, we're going to sort of get a new coordinate system. And we can look at the parallelograms there, and they're sort of going to be a warped version of the original parallelograms in a very sort of predictable way. You'll see what I mean. So think about this point here. Notice that in this picture, we have these dotted squares like this. And in a sense, they are telling us about the kind of Cartesian coordinates of things. You know, that people speak about the coordinate grid, you know, a square grid. So we have this point, for example, we can see by looking at these squares that this is one step to the right and 3 steps up from the origin. In other words, there's going to be this vector here, which we can write as 1, 3. So to get from the origin to this point here, we go 1 step to the right and we go 3 steps up. And so notice then that really we can describe how to get to this point using these parallelograms here. So squares are certain kinds of parallelograms. And really the point here, I'll just say it very quickly, is that these squares, when we apply our linear map, well, this point here is going to get sent to this point here, and this point here is going to get sent to this point here. And then you can see that the squares that I've just drawn are going to get sent to these different parallelograms here. And you can see that basically doing a similar thing to what we're doing here with these red parallelograms to get from this far corner here to this far corner here. If we do a similar thing with the green stuff, then we get from here to here, and that's basically telling us what the image of this point here is going to be under our linear map. It's going to be this point here. Well, okay, let's work through this more slowly. That was too fast. So basically, what I'm saying is that what we're interested in is determining the image of this vector here, 1, 3. We want to figure out what is m of 1, 3. What can we say about this vector? Well, how can we form it? Well, we can form it by taking one of these vectors and adding 3 of these vectors to it. So let's write that then. We can write that this is equal to 1, 0 plus 3 times 0, 1. Now here's the thing. What we want to do is we want to do a linear map on this. And it's a consequence of the sort of geometry and this idea of grids of parallel, and this idea of these sort of grids of parallelograms, that we have 2 different laws that always hold for our linear maps. Firstly, maybe the most important law is that when we do our linear map to a sum of vectors, could be any vectors, but let's look at this case. Then the result is just going to be the result of doing the linear map to the things in the sum and then adding those together afterwards. So in other words, we can add the vectors first and then apply the map, or we can apply the map first and then add the images of the vectors. We'll get the same result either way. So in other words, this is going to be equal to m of 1, 0 plus m of 3 times 0, 1. And then the second rule, the second sort of, I mean, this is usually thought of as one of the algebraic rules of linear maps, is that when we have a linear map, which is applied to a scalar times a vector, then we can pull that scalar outside of the linear map. So in other words, this thing here is the same thing as 3 times m of 0, 1. So this whole thing we can write like this. And so let's think about what this means geometrically, because I think you'll find that this makes a lot of sense geometrically. What we're saying is that if we want to find out where this gets sent, then we see how this is built, and we see that it's built out of one of these vectors and 3 of these vectors. And then we just look at how each of those is going to get mapped. So let's make this a bit squiggly here. So this squiggly one is going to get sent over here, and the other one is sent here. So we want to have 3 of these and 1 of these squiggly ones, and we end up getting this. So you see that these kind of rules that, you know, the image of the sum is the sum of the images, and the image of the scaled vector is the scaling of the image of the vector. These kind of rules, they're basically telling us how to understand how our linear map works across the entire plane. So basically what I'm trying to convey here, which is sort of obvious from this picture, is that once we fix where the vector 1, 0 and the vector 0, 1 get sent by our linear map, the way the linear map works on everything else is fixed. And so think about it. How many numbers do we need to specify where 0, 1 and 1, 0 get sent? Well, we need a x and a y coordinate for each. So we need 4 numbers. So that's our matrix, right? That literally is the matrix which describes the linear map. So this is quite extraordinary. So the normal way that people learn about matrices is that they say, okay, a matrix, a 2 by 2 matrix is just 4 numbers. And then there's a rule that if you have a so-called column vector, so that's two numbers which you write like this, then there's something that that matrix does to that column vector. It turns one column vector into another one. And so in this case, M would be this matrix here, A, B, C, D. And we can ask what that does to a column vector. And people normally think of this just in terms of algebra. They say, okay, just memorize this formula. It's AX plus BY. That's the first entry in the output. And the second entry is CX plus DY. So you can think of it like that. But now, hopefully, you can see that there's a bit more geometry to be appreciated here. Because look at this. What is this vector here? M of 1, 0. Well, it's one step to the right and one step down. So it's the vector 1, minus 1. What about this one here? M, 0, 1. Well, this is the vector 2, 1. And look at this. This is the matrix that we're multiplying by. This is the matrix we get by sticking together these two. So if we look at the image of 1, 0, that's 1 minus 1. If we look at the image of 0, 1, that's 2, 1. So that gives us our matrix. And then we're interested in what happened to this point here, this point 1, 3. And then if we apply this, this matrix multiplication here, and what do we get? 7, 2. And where is the image of this point under M? It's here at the coordinates 7, 2. So you can see that this all works out, and it really ties together into a very pleasant sort of geometric story. And so a lot of what I've said is really summarized by this sort of algebra here. And it's basically what I've just been talking about. If you like, you can just take this as the definition of what happens to a vector xy when we multiply it by this matrix A, B, C, D. So that's fine. But like I say, I want to sort of emphasize the geometric connections here. So when we have xy, then we can sort of break that down and see how we can sort of rebuild that by adding together these sort of primitive vectors, 1, 0 and 0, 1. And so we get in general that we can write xy as the vector 1, 0 scaled by x plus the vector 0, 1 scaled by y. And then we have these two key features of what happens when we apply our linear map M to vectors. One of them is that when we apply M to these two vectors added together, then the result is just what we get if we apply M to the first vector added to what we get if we apply M to the second vector. And you can think of that in terms of those grids as to say, well, if we know we can get to xy by going so far to the right and so far up, well, we see what happens to those primitive vectors under the linear map. And those make these sort of grids of parallelograms, and we just sort of go the corresponding number of steps, but in that sort of transformed grid. And that's basically what this line is telling us. And so what it's really telling us is that to find out where xy gets mapped, we just need to know where 1, 0 gets mapped and where 0, 1 gets mapped, and then scale those by the corresponding x and y numbers. And so you can see by this equation here that really the way that our matrix acts is really totally defined by where it sends the vector 1, 0 and where it sends the vector 0, 1. So why don't we make some special names for those images? We'll call the first one AC and the second one BD. And then this formula here just turns into this sort of formula here. And actually, we can work out what this is. It's just we're allowed to take these scalars inside the vectors, and then we add what's upstairs and add what's downstairs, and we get this. And so now we have this beautiful formula here, which is telling us what happens when we apply our matrix to x and y. And you can see that the result that we get here it just depends on these numbers, A, B, C, and D. So actually, why not actually give our linear map the name ABCD, right? So because those four numbers really define everything about how it works, like why don't we actually call the map ABCD? And if you like, you can think of that as a sort of a backwards definition of a matrix, if you like. Okay, then, so now we've properly defined what we're talking about. We're almost ready to dive into the fascinating sort of behavior that we can generate using these matrices. Just before that, we need to cover the notion of matrix multiplication. So some of you may have already seen this thing before. Some of you might be more comfortable with it from a purely algebraic point of view. And so from that point of view, basically the idea is that when we multiply this matrix by this matrix, we get this matrix as a result. And so there's this sort of operation in maths called the dot product. And the idea is that when you have a vector, or a list of, in this case, two elements and another list of two elements, we can do their dot product. And that just means we multiply together the first two elements and multiply together the second two elements and add those things together. So we get this. So basically, sort of algebraically speaking, we multiply these matrices here by doing the dot products of this vector with this vector, and that goes at the top left. And then we do the dot products of this with this, and that goes here. And we do the dot product of this with this, that goes here. And finally, this with this goes here. So that's the basic idea, and this is the most interesting way of composing these matrices to make other matrices. So let's see a bit more about the sort of justification for that formula. So basically, the notion is this. What we have is the plane here, r squared. So r squared just means the set of pairs of numbers, like an x coordinate and a y coordinate. And those will give us a vector, which is pointing out of the origin. So we consider a sort of general vector, x, y. And we have this sort of setup, and then what we're going to do is we're going to apply this linear map. So we have this linear map described by this matrix here, A, B, C, D, and that's going to transform this xy into this other vector here. We've already seen what a matrix does to a vector. It turns it into this, ax plus by, cx plus dy. So let's give those two things special names. We're going to call those x tilde and y tilde. So x tilde is ax plus by. Okay, so the next thing we're going to do is we're going to then apply another linear map. So here we have another linear map, this matrix with potentially different numbers in it, a dash, b dash, c dash, and d dash. And we're going to apply that to this vector up here. And so, of course, this is going to be the result. And so what we can do, since we know what x tilde and y tilde are, we can expand out this result and we get this. And then by examining this result here, we notice that it can be obtained just by getting our starting vector and just using this green matrix here. So basically what I'm saying is that if we want to apply this matrix and then apply this matrix, we can do that in this sort of two-step manner, or we can just do it all in one step by applying this matrix here, and we get the same result. So basically, composing this matrix and then this matrix results in this matrix. Now, when we write this kind of stuff, we write it in this funny kind of order. So you should think that we're sort of applying this matrix first, and then we're applying this matrix. And this is the resultant matrix. So this is similar to, in category theory, the way that we write composition. And if you want to make more sense of the ordering here, think about it like this. We start with this vector xy. So that goes on the right. So you can read this as follows. If we start with xy, and then we apply this matrix here, then we get the same result as if we start with xy, and then we apply this matrix here, and then we apply this matrix here. So it's this usual, I've heard it referred to as the greatest mistake in mathematics, this idea that we think about function application working from the right to the left, whereas we normally write things working from the left to the right. So this is perhaps some kind of unfortunate convention which has become very mainstream these days. So that's matrix multiplication, and it basically tells us how we can combine these matrices and what sort of other operations they form, what other linear maps they make. So it's pretty much the same idea as applying one function and then another function. It's that idea, but in terms of linear maps. So we're interested in composing or multiplying our matrices according to that kind of formula. And it turns out that with respect to that kind of operation, there's a very special matrix, and it's sometimes called I, or the identity matrix. So it looks like this. And it's easy to check. I invite you to check for yourself that basically when we multiply this identity matrix by another matrix, any other matrix, we just get that other matrix back again. So this is sort of like the neutral element with respect to matrix multiplication. Notice that the notation here looks quite a lot like a 1. And you can think of this as a sort of higher dimensional analog of the notion that multiplying a number by 1 just returns that number. So we're interested in all of these 2x2 matrices, and we have this notion of matrix multiplication. We also have this identity matrix, and it turns out that that structure forms something called a monoid. Now, if you don't know what a monoid is, don't worry about it, but there we go. So that's one operation that we're interested in with these matrices. Here's another one. This is called matrix addition. And this is a much simpler one to understand. Basically, when we add two matrices together, we just add the corresponding components. So we add the things at the top left to get the entry in the top left of the resulting matrix, and similarly for the other 4, and similarly for the other 3 positions in the matrix. And once again, there's this sort of matrix which is sort of neutral with respect to this operation. It's the matrix full of zeros. Adding that to something obviously isn't going to change the matrix. So that's it. That's all the groundwork done. Now let's get into some of the fascinating things that we can do with this matrix algebra. So this is one of the most intriguing ones. This is this matrix which I'm going to call suggestively epsilon. Okay, so notice that epsilon is not the zero matrix, but it does have a feature that's kind of similar to the zero matrix. It has the feature that if we square it, meaning we multiply matrix epsilon by epsilon, well, if we work it out, we're going to be dotting this with this. That's going to give 0. That goes up here. Dotting this with this gives 0. And dotting this with this gives 0, and this with this gives 0. So yes, when we multiply these two things together, we get zeros. So if you've watched my videos on smooth spaces, you might find this particularly intriguing, because basically what we have here is a matrix which is acting like a Nil-square infinitesimal. So this is a really, really remarkable thing. When you're doing calculus, you like this idea that you have these quantities that are so small that even though they're there, and you want them to be there so you can measure gradients and curves and so on, but you also want them to vanish when you square them. And normally this is done in a sort of approximate manner. One says, okay, let's imagine that we have this number and we're going to make it smaller and smaller, and then okay, we can neglect the square of it because it's so small. And this is a kind of this is a kind of approach that has caused a lot of mathematicians and philosophers headaches over the years, because one has to set up all sorts of complicated analysis ideas to make that kind of thing happen. And so there's a sort of alternative stream of thought that says, well, can we get something that acts like these Nil-square infinitesimals sort of directly? And there's various ways to do that. This idea of using these smooth spaces and this sort of topos of smooth spaces that I mentioned in other videos is one possible approach. But here's another one, which I would say is is in a sense a lot simpler. And there's really there's no ambiguity, there's no messing about with the laws of logic or appealing to intuition about infinitesimally small things. This is just simply a matrix. It's just a nuts and bolts matrix that literally has the property that if you times it by itself, you get zero. And it's actually possible to use this kind of machinery to start building calculus. So Norman Wildberger has some great videos on treatments of infinitesimals where he talks about this approach. But just to show you the basic idea, we can consider matrices of this form. So here, A and B are just numbers. And so if we do A times the identity matrix, that's this, and B times epsilon, that's this. And then we know how to add matrices together, and the result is this. So on one hand, we have this kind of quantity here, which looks very much like the expression for something called a dual number. So these dual numbers, they have these real numbers, which are multipliers here, but the first multiplier A is just multiplying I, so you can think of this as just the number A. But then we have this second part of the number, which is this other number B multiplied by this Nil-square infinitesimal, epsilon. So you can sort of visualize these numbers as having like A big units and then B little infinitesimal bits extra. And indeed, we can do sort of algebra with these things. So if we take two of these expressions, well, we can add them together. And there's no mystery in how we add them together because really, this is just shorthand for matrix expressions. So we know that this matrix on the left here is this, and this matrix here is here, and we know how to add them. And you can see that the way that we're adding them is the way that you'd expect to add these sorts of dual numbers. We just add the sort of large part and add the small part and collect those together. But where it gets really interesting is that we can also multiply these dual numbers together. So look at this. If we multiply this dual number here by this dual number here, well, we can do it just using the sort of algebra of dual numbers, right? Like, it's very similar to how you manipulate complex numbers. You just say, okay, I'm going to multiply these expressions out like I know how to multiply bracketed expressions. And then I'm going to remember that epsilon times epsilon is 0. And so if you do that, this is multiplying out the brackets, and then we know that this here should be 0. Well, then this is the result. But look, this is just the same as what you get when you do this matrix multiplication here. So we really get this formula being justified to us by the matrix calculus. So this is the kind of thing that you see with this sort of matrix algebra. Time and time again, we see these ideas from ordinary algebra, ideas which have sometimes been viewed with suspicion because they're involving crazy things like infinitesimals or imaginary numbers. And we then see that there are matrices that make these things happen without introducing any ambiguity. It's really quite extraordinary. And there's other really remarkable things about these Nil-square infinitesimals. So if we have a matrix like this one here, we can make another matrix called its transpose. We basically get that by reflecting the matrix in this diagonal line, if you like. So the rows and the columns kind of swap their roles. And so if we take the transpose of this epsilon, then we get this other matrix here that we call epsilon transpose or epsilon t. And this is another Nil-square infinitesimal. But there's something that's really kind of beautiful that happens here, which I think to me almost has some kind of almost mystical kind of interpretation, which is that we have these two matrices here, epsilon and epsilon transpose, and these are really representing infinitesimals in some way, but they're different kinds of infinitesimals. And then in some sense, we can use these two things to build up all the other matrices. So it's much like certain ideas that you can build up all the geometric objects, starting with the ideas of infinitesimals. Now, the way this works is like this. If we consider epsilon multiplied by epsilon transpose, well, if we work it out, we get this matrix here, which has a 1 at the top left. Similarly, if we multiply them the other way around, we get this matrix here with a 1 at the bottom right. Well, we could add these two things together and we get the identity matrix. Actually, if you look at it, we have all of the 4 matrices that we need to be able to make any other matrix. So if we take some kind of a combination of these 4 matrices that I've circled, and we multiply them by different scalars and add them together, we can make any other matrix we like. So in some sense, starting with these two, you can build up all of the other matrices. And there's some fascinating connections here with ideas from subjects like geometric algebra. If I can think on, I'll add a link in the description about that, because there's a remarkable page which talks about how you can kick off thinking about geometric algebra, starting from this kind of concept. And so, in a nutshell, what I want to say is that, the space of these 2x2 matrices is extremely rich if you take a view of it as a sort of cohesive whole, because we can select certain subfamilies of these matrices, for example, matrices of this kind of form. And these are forming a sort of submonoid, okay? And these are forming a sort of submonoid. We can multiply any two of these matrices together and we get another matrix of this form. So if you find the whole space of 2x2 matrices too bewildering, you can focus your attention on these kind of matrices, and you can ask all sorts of questions and try and understand this sort of submonoid in its own right. And when I say a monoid, I just mean something where we have an identity element, that's the identity matrix for us, and we also have that when we have 3 of these elements, for us these are going to be matrices, if you multiply A and B and then C, you get the same result as if you do A times BC. So let me show you another few of these sort of intriguing submonoids that we find in this space of 2x2 matrices. These kind of matrices here, we can consider these kind of matrices here. So if we just pick any 2 real numbers, A and B, then we can form a matrix like this. And we can consider all of the matrices like this. And again, these are going to form a sort of submonoid. So the way you can read this is it's the set of all matrices A, B, B, A, such that A and B are in the real numbers. And I urge you to look at these, and it's a really fun exercise to look at things like this, and you can apply many of the methods that I'm going to talk about in this video, and you can try and understand the space of all of these matrices. It's going to be a sort of 2-dimensional space now, because there are these 2 real numbers that we can vary to sweep over this whole set of these matrices. Here's another one. These are called upper triangular matrices. And again, these are forming a kind of submonoid. This is a 3-dimensional space. And you can see that it's going to contain these kind of matrices here that are representing these dual numbers. So here's another thing I wanted to show you. Again, you might want to study this later on. What about the square root of 2? We're sort of doing a tour of historically controversial objects in mathematics, right? So what's the square root of 2? Well, it's a number that if we square it, we get 2. Well, how do we talk about 2 with matrices? Well, we can talk about 2 times the identity matrix. That's kind of acting like a 2. So is there a matrix that if we square it, we get this? And indeed there is. Let's consider this one here. If we multiply it by itself, then indeed we get 2 times the identity matrix. So this is really remarkable, because here we're having something that acts like the square root of 2, but we're not even using fractions. So somehow we're getting this kind of mysterious behavior of a quantity that you can square and get to without having to talk about anything like irrational numbers. Okay, then. So one of the most extraordinary things that I want to explore is this connection between these 2x2 matrices and complex numbers. So take a look at this matrix. I call it little I. And if you know about complex numbers, then you know that the main sort of question that gets us into all of this world of complex numbers is there a number that squares to -1? And of course, there isn't an ordinary number that has that feature. But if we imagine that there is, and we give it the name little I, well, then we can get complex numbers. And these complex numbers, they have like a real part, which is just an ordinary number, and then they have a complex, and then they have an imaginary part that's another number times I. So they have this form a plus b little I. So it turns out that we can access this world of complex numbers basically just by considering these 2x2 matrices. So the key to all this is to think about this matrix here, which I'm going to suggestively call little I. And now let's ask ourselves, what happens if we consider little I squared? Well, that's little I times little I, and we can write out the matrix multiplication here, and we can write out the matrix multiplication here, and what do we find? Well, we find that the result is equal to -1 times our identity matrix. So this is really remarkable. What we've done is we found the matrix which squares to basically the matrix equivalent of -1. And it gets better because actually what we can then do in a similar way to what we did with the dual numbers, we can consider matrices of this kind of form. So it's A times the identity matrix plus B times little I. And such a matrix has this kind of form. And it basically works exactly like this kind of complex number, the kind of thing that people would normally write in ordinary maths. They'd write this kind of thing as A plus B times I. So here, A and B would be real numbers, but this is a number of the form A plus B times the square root of -1, if you like. And, using complex numbers has been a remarkable leap forwards in mathematics. They're one of these things, again, which sort of, when one first hears about complex numbers, and they're like, and it sort of raises these philosophical issues in a sense, right? Like, how can there be a square root of -1? Show me the square root of -1. People can say things like that. But once again, our 2x2 matrices sort of come to the rescue, and they provide us with these concrete matrices that have the features that we want them to have. And so the story is very similar to what we saw with the dual numbers. We can now consider expressions of this kind of form, A times the identity matrix plus B times little I. And if we add one such expression to another, then they add as you'd imagine. We add the real parts and we add the complex. We add the real parts and we add the imaginary parts. And this is all mirrored by the way that these matrices work under addition. So if we rewrite these expressions in this kind of form, we see that that alternative form acts in the same kind of way. And also, of course, we get the behavior we'd expect when we multiply these kind of complex numbers together. So if we multiply this expression by this expression, well, if these are going to act like complex numbers, then we'd expect that we can sort of calculate this out. Then we'd expect that we can sort of calculate this out just by multiplying using algebraic rules, and then remembering that little I times little I is -1. So this is the answer we'd expect if we're working with complex numbers. But once again, if we actually say, okay, these are really matrices, and this is really the manipulation that we're doing, well, it exactly matches the result that we'd expect. This is another one of these sort of complex number representing matrices, and this is really just a representation of this complex number here. If we're doing this right, we should put these identity matrices in here. So this connection between 2 by 2 matrices and complex numbers is extremely deep, and it really gives us lots of ways to make connections with things that are happening elsewhere in group theory and things which are happening in physics and all sorts. Complex numbers are a very interesting sort of beast, not something that I've spoken about too much on my channel, but they're the kind of thing that seem very kind of peculiar when you first learn about them, but it's really remarkable how much the universe seems to sort of use complex numbers in the laws of physics. They appear in quantum mechanics, they appear in special relativity, they appear even in relatively mundane situations, like if you try and understand the motion of a spring or a harmonic oscillator, complex numbers can appear to make much more sense of situations like that. And so what we're really seeing here is that if we consider these sort of 2 by 2 matrices here of this kind of form, we're seeing that these are really representing the usual sort of complex numbers, the kind of thing that we'd write as A plus BI. So let me just take a little bit of a tangent into how complex numbers are related to trigonometry and angles, because there's some really remarkable connections here, and they have to do with thinking about ideas like circular rotation in terms of these matrices. So in particular, let's think about a complex number, so something that we could write as A plus BI, or, in the notation that I've been advocating, A times identity matrix plus B times little I. Well, we can think of such a thing as a number on the complex plane. You see, it has a real part and it has a complex part. And so if we think of those as the sort of x and y coordinates, then we can think of our number, z, as a point on this plane, which we call the complex plane. So if we call this complex number z, then there's another way that we can think about it. So it's very similar to how we can talk about where a point is on the plane using x and y coordinates, or we can talk about where a point on the plane is using so-called polar coordinates. That means that we refer to a sort of angle that we have to turn about, and then an amount that we have to multiply this sort of unit vector to get to the point where we're interested in. And so the basic gist of this is that we can rewrite this number like this, as capital R cosine theta plus capital R sine theta times I. So here, when we're multiplying by I, we're basically just saying that we're talking about the sort of upwards direction here on the plane. And so the way that you can make sense of this kind of formula here is that you can think of R as this sort of distance that our point Z is away from the origin, 0. And you can think of theta here as the angle and you can think of theta here as this angle from the x-axis to the vector that's pointing at our z. So basically, if you get a unit vector, you rotate it up by theta, and then you rescale it by timesing it by r, you get to z. So that's basically the point. I've just got a few more sort of details here, just for those that like their trigonometry. If you're not very familiar with this stuff, don't worry, it's not going to play such an essential role. So basically what I'm saying is that we have this number z, and this number across the bottom here, this is A, and this number up here, this is B. And so we sometimes call A the real part of Z, and B the imaginary part of Z. And also this radius R, well, we can get that from Pythagoras' theorem. R squared is A squared plus B squared. So that allows us to determine what this non-negative number capital R is. And then we can rewrite our quantity Z in this kind of form. And, if you like, this is the formula which allows you to determine what this angle theta should be. So this is really worth doing because we're interested in these kind of matrices here. And so if we do these sorts of substitutions here, well, we can write A as R times cosine theta and B as R times sine theta. And so we can write this matrix here in this kind of form. So, okay, this R here is just a sort of scalar. If you like, you can take it inside of the brackets and multiply it by each of the four entries. Anyway, this turns out to be a really pleasant form for thinking about these matrices, because let's introduce some shorthand here. We're gonna call this m theta r. So that's just a sort of shorthand for this sort of matrix here. And now the really beautiful thing is that the way that matrix multiplication works is given to us by this really lovely simple formula here. So it turns out that basically when we multiply these two matrices here, that corresponds to multiplying the corresponding complex numbers. And if you know about complex numbers, you'll know that when you're multiplying the complex numbers, basically there's a really easy way to do that. If you're expressing these complex numbers in terms of r and theta, then you just sort of add the angles together of your two complex numbers, and then you multiply together these r values here. So this is the sort of magical formula, which is telling us how we can. So this is the sort of magical formula here, which is telling us, well, it's telling us how we can multiply complex numbers. It's also telling us how we can multiply these kind of matrices here, because that's basically the same thing. Now, I should also just say that when I'm adding these angles here, of course, when you're adding angles, once you go around a full circle, you're back to zero again. So let's take the convention that there are these 2 pi radians in a full circle. So after you've increased theta from 0 to 2 pi, it goes back to 0 again. And so this really gives us a very lovely kind of substructure here that we can look at, and it's sometimes called the circle group. Okay, so basically the point here is that we can consider matrices of this kind of form. So these are basically these numbers that are representing, so these are basically these matrices that are representing complex numbers, but here that capital R is equal to 1. Okay, so basically what we can think of these things as is we can think of them as points on the unit circle here. So they're really defined by an angle, this angle theta here that we're putting in here. And the beautiful thing here is that if we're multiplying two of these matrices together, well, we just add the corresponding angles. So we have that if we want to multiply m theta 1 with m phi 1, the result is just m of theta plus phi, comma 1. And this is just what you see when you're multiplying these complex numbers that have an absolute value of 1. So this is really beautiful because it's connecting together loads of really interesting things in geometry now. We're getting the connection between the complex numbers, these special 2x2 matrices, and the circle group. And this kind of group is also sometimes called SO2. That stands for the special orthogonal group with respect to 2. I'm going to come back to that later. So you can see that we're gathering momentum here, and we're starting to make connections with group theory. So basically, what I want to start talking about now are these special sort of subsets of this space of 2x2 matrices that have the feature that they act like a group when we multiply the matrices. So I'll explain about what groups are momentarily, but the really important thing is that we want to be able to invert these matrices. So sometimes if we have a matrix M, then there's going to be another matrix which we can write as m to the minus 1. and it's called the inverse of M. If it exists, it's uniquely defined. And it's defined to have this property here, that basically, if we multiply the matrix by the inverse matrix, we get the identity matrix. Okay, this is like very similar to how if you have a number that's not zero, you can it's very similar to how, you know, if you have 2 times a half, you get 1. So we're going to be really interested in when these matrices have inverses, because when that happens, we're going to see these kind of group structures emerge. So in order to study that, there's this quantity here, and this is a number that we can associate with a matrix. And it's really important. It's called the determinant of a matrix. So if we have a matrix M, then the determinant is basically defined as this: A times D take away B times C. So it's a number and it's very easy to compute, but it also has really important sort of geometric significance. So the best way to understand what a determinant is geometrically is basically that it's the area inside this kind of parallelogram here. So if you think back to the beginning of the video, you'll notice that the form of these two vectors here, M10 and M01, basically the form of these column vectors, is really important. It basically defines everything about how this matrix works on the plane. And the determinant here actually measures the area which is inside this sort of parallelogram that I'm drawing here. So there's a little bit of subtlety here. If you imagine taking this picture and then moving the blue and the purple arrow so that they kind of go through each other, then this area would actually be deemed negative. So this is a so-called signed area. And I'm not going to get too much into the geometric connections here. I'll put a link to a wonderful video that derives why it is that this determinant is the area of this parallelogram. It's very worth watching. But the point for us is that looking at the determinant of a matrix tells us if we can invert it. So if we go back to this picture here, the determinant is really measuring the area inside this parallelogram here. And you can see that applying this sort of matrix transform to our plane is really just sort of warping these parallelograms here. And perhaps you can imagine that there should be another sort of transformation, which is going to get us back to the nice kind of rectilinear setup that we had at the beginning. Now, that's always going to be true, except when these two vectors here are pointing in the same direction as each other or pointing in opposite directions. And those are going to be exactly the cases where that parallelogram formed here has a zero area. Okay, so what we basically see is this remarkable result, which is that basically a matrix like this is going to be invertible in the sense that the inverse of M exists if and only if the determinant of that matrix is not zero. Okay, so as long as that determinant's not zero, that parallelogram has an area. That means that those two vectors are not going to be pointing, they're not going to be sort of collinear. And that means that we can invert the matrix. And this is actually the formula that tells us what the inverse of the matrix will be. So it's a nice exercise that you can do basically to check that this does indeed work. So you can see why we want this determinant to not be zero here, because what we're doing is multiplying by 1 over the determinant. That's the sort of scalar that we're rescaling this switched about matrix by. And so you can easily check that in this case, if you just write down the algebra, that we have M times M inverse is M inverse times M is identity. So I urge you to check that because it's a very important exercise. And so with all that said, we can now introduce a really, really beautiful mathematical structure. And it's called the general linear group. So this is a really, really lovely thing. Very important for physics, very important for geometry, connecting together matrix algebra and group theory It's a really, really beautiful thing. So firstly, let's have a bit of notation here. I'm going to write r to the power of 2 times 2 to denote this whole set of 2 by 2 matrices. So it's this. So in a sense, this is the object of study of our video here. But now let's consider a certain subset of these matrices, and they're going to be the ones which are invertible. Okay, so this is called the general linear group 2R. And we can define it like this. It's the set of all of the 2 by 2 matrices that have a determinant which is not 0. So it's a beautiful thing that actually this set of matrices is forming one of these structures which is called a group. Okay, so what is a group? Well, a group basically is where we have a load of elements and we have, so a group basically is where we have a load of elements and we have a sort of operation. I usually won't write a symbol, but I'll write a little dot for the purposes of explaining this. So we have this sort of binary operation dot. So we have this sort of binary operation dot, which, you know, we can take a couple of elements and we can dot them together and get a new element. And then we require that this operation has to be associative, meaning that this is always equal to this. And it has to have a sort of neutral element. For us, this is going to be the identity matrix. So we have to have this. And then every element has to have an inverse, which has the feature that if we dot the original thing with the inverse, we get the identity matrix. We get this identity element. So that's what a group is. And it turns out that the general linear group is a group. So this is something that you can check for yourself. Maybe the most intricate part of this is to assure yourself that if you multiply a couple of matrices together inside this general linear group, you'll get another member of the general linear group. But we can see that this is true by this lovely formula here. And it says that the determinant of the product of two matrices is always the product of the determinants of those two matrices. So basically what we have here, what I'm sort of trying to introduce with a bit of fanfare, is this general linear group, because this is a really important object in mathematics. And it basically consists of all of the matrices that you can invert, and then our group operation is just matrix multiplication. So this is really remarkable because we can now start to understand something about the sort of global structure of all of these 2 by 2 matrices. So we have the all of these 2 by 2 matrices, and now we see that some of them are invertible. So inside this set of all of the 2 by 2 matrices, we have this general linear group, which consists of the matrices that can be inverted. And we can see what they are geometrically, as I was showing before. Basically, the members of the general linear group are these normal sorts of matrices that have the feature that these two vectors are pointing in different directions. And then the special cases, the sort of degenerate cases, if you like, are these kind of cases where these vectors are pointing in the same direction as each other. And then, of course, you can't undo that linear map. Okay, then, so that's the main conceptual challenge out of the way, which is appreciating the definition of this general linear group. Basically, just the set of invertible 2 by 2 matrices. And hopefully you can see that this is important. This is basically the way that we can do these kind of linear transformations of the plane in invertible manners. But now we have this, and this is sometimes called a matrix group. So you find in physics, for example, there are many of these sort of groups of matrices which are very important for understanding reality, and this is one of them. And now that we have this, we can look at some interesting kinds of subgroups of this general linear group. So this is one of the most important ones. It's sometimes called the special linear group. So this is the set of all of these 2 by 2 matrices which have a determinant of 1. Okay, so not only are these invertible, but if you think about those sort of parallelograms and things, basically the parallelogram that is generated by the sort of transformed unit vectors also has an area of 1, just like the kind of squares that we started with. So these are even more special. And so the special linear group sits inside the general linear group, and it's quite a lot easier to understand in some ways, but in other ways, it's kind of, at least in this case with these real matrices, a lot of behavior that we see in the special linear group is just a kind of quite similar to the behavior of the general linear group. We'll get onto this later, because it turns out that actually there's a really beautiful three-dimensional manifold which corresponds to this special linear group. And it really gives us a lovely kind of geometric picture of all of these different matrices that have a determinant 1, and somehow they all form into one particular space. We're going to see that later. So what kind of matrices have a determinant equal to 1? Well, we've already encountered some matrices that have that kind of feature. Look at these kind of matrices here. I was saying that these were this kind of rotation matrices that corresponded to this sort of unit circle. So such a matrix can be written like this. And also, we can write such a matrix as m theta comma 1. I'll sometimes just write that as m theta. So I don't write that the sort of capital R absolute value is 1. That should be clear. But it's easy to see that a matrix of this kind of form, of which this is shorthand, for which this is, so basically this is shorthand for this, and it's easy to see that a matrix of this kind of form has a determinant of 1, because if we just calculate the determinant, it's this times this, take away this times this. Well, that's going to be cosine theta squared plus sine theta squared, and we know that that's 1. It's basically our Pythagorean theorem. So what we basically have is that this is going to be a certain subgroup of our special linear group. As I said before, it has a name. It's called SO2. We're going to see more about that later. Just to kind of whet your appetite for it, think about these 3 points here on the circle. So here we have the unit circle, and we have these 3 points here, which are obtained by starting off over here and then doing a third of a turn, and then also looking at this one obtained by doing 2/3 of a turn. And so it turns out that these 3 elements here, well, they're going to actually form a subgroup of this group here, right? Because what's happening in this group here is that we have all of the different sorts of angles of our circle, and then our group operation or our matrix multiplication basically corresponds to adding those angles. So that's like a kind of continuous view of the whole circle. Whereas what we have here is just these 3 points which are equally spaced around the circle. And you'll see that these are basically corresponding to the 3 vertices of an equilateral triangle. They would if I was drawing them properly. And so basically what we have here is this sort of equilateral triangle, and then we can do rotations of it by either a third of a turn or 2/3 of a turn. And so this is also forming a sort of subgroup here. And actually, if you think about it, it really corresponds to the same kind of group that we have when we look at what we have with our integers when we add them together, mod 3. So this is an example of a sort of cyclic group. And of course, you'll see other similar groups if you look at other polygons and you think about a regular polygon with a certain number of sides and what happens to it when you do rotations. So, okay, I keep referring to this thing called SO2. I've told you now several times that it basically corresponds to the circle. But let me try and explain now a bit of this terminology. This might seem a little bit cryptic. If this seems a little bit cryptic, don't worry, it's not something that I'm really going to build on. But basically, this general linear group, this consists of all of these invertible matrices. So this is a big group of matrices, and there are various interesting subgroups. So one of them is called the orthogonal group. It's called O2. Now that consists of all of these invertible matrices that have the feature that their inverse is equal to their transpose. Remember, I defined the transpose of a matrix earlier. It's what you get basically by sort of reflecting the matrix across the diagonal line in some sense. So this is called the orthogonal group. And basically, you can think of it as consisting of all of these kind of matrices that represent and basically you can think of it as corresponding to all these matrices that represent the unit circle, the kind of thing that I was just looking at, together with this other operation that can kind of flip over a circle. So if you get a cardboard circle, a circular disc, and you think about the operations that you can do where you can rotate the disc around and you can also flip the disc over, that basically will look like this group O2. We're going to come back to that later. And so, okay, what is SO2? Well, that's the special orthogonal group. So basically, SO2 is the sort of intersection of O2 with our special linear group. In other words, SO2 corresponds to the matrices in O2 that have a determinant 1. And we've already seen SO2 several times. Basically, it corresponds to all of these matrices that basically represent points on the unit circle. So we're already developing a fairly interesting picture of these 2x2 matrices. Okay, we can see lots of things going on here. We have the whole space of the 2x2 matrices, and then we have the sort of invertible ones here. And these are the ones with non-zero determinants. And then out of these, we can see even more kind of special things. For example, we have this special linear group, and this consists of all the matrices that have a determinant of 1. And then we have this O2 here. This consists of these invertible matrices that's inverse is equal to the transpose. And then the intersection of these two is this SO2 here. So we can see that SO2 corresponds to this unit circle as follows, right? So we know that this matrix here is going to be in SO2 if and only if it's got determinant 1 and its inverse, which we have a formula for like this, is equal to the transpose of the matrix, which is here. Well, if you think about it, that's going to imply that A is equal to D and C is equal to minus B. So we know that the matrix has to have this kind of form, and also it has to have the feature that, its determinant is 1. Well, that's just going to be A times A plus B times B. So there we have it. This is SO2. And it basically corresponds to the sort of group of rotations that you can do in two-dimensional space. So now we understand sort of this part of our space of matrices. Can we go further? Can we understand what O2 is? Well, I'm just going to briefly sketch how we can think about O2. It's quite a nice exercise to fill in the details here. Basically, a lot of it corresponds to thinking about this matrix here, which I'm going to call J. So J has the interesting property that if we multiply J by itself, we get the identity matrix. And basically, you can think of J sort of geometrically as sort of switching around the roles of the X and the Y axis. Okay, so it's going to send a vector xy to the vector yx. And so it has this interesting kind of property that it's sort of, in some sense, it's sort of flipping over the plane. So if we want to do the identity map, we can just put these images of these primitive vectors on top of where they start. But if we want to swap around the roles of I and j, well, we can do that by moving things like this. And you see we've flipped around the plane here. And now we've sort of reversed the roles of the x and the y axis in some sense. So you can see that what's happening here is essentially that we're sort of reflecting everything in the plane in this diagonal line. And hopefully you can also imagine that if we were to do this twice, we'd get back to the identity. And this kind of explains this formula that j times j is the identity. But it turns out that using this j really helps us to understand what this orthogonal group O2 is. So I'm not going to justify all the math here, but basically you can get O2 by taking this SO2, which if you remember just consists of all of these basic rotation matrices, and then you can get all of those, and then you can get each of those multiplied by a j, and you can sort of take the union of those. So basically what we have is all of the different rotation operations and all of the things that we can get by doing a rotation and then flipping our thing upside down, if you like. So this is what SO2 looks like. It's a lovely exercise to see if you can check that this is a group and you can understand how multiplication of elements works and so on. But I just wanted to show you a really interesting kind of subgroup of SO2. And it's basically consisting of these things. So if you remember from before, I was talking about this sort of this substructure inside SO2, which basically is where we have these kind of discrete rotations which correspond to the rotational symmetries of the equilateral triangle. But if you have like a cardboard equilateral triangle, yes, you can do these 1/3 or 2/3 rotations, which leave it looking the same, but you can also flip it over, right? You can take an equilateral triangle and you can sort of flip it upside down like that. And so it turns out that if we think about this structure inside O2, so not only do we have these familiar elements, but we also have these three here, then this is going to form a group. And it's actually going to correspond to the group of all of the symmetries of the triangle, like including the ones that involve flipping over the triangle. And so this is an example of one of these kind of dihedral groups where we're looking at three-sided regular polygons. It also corresponds to a famous group called S3. The symmetric group, or the group of permutations of three elements. So we're making some good progress here. And we've almost got enough algebraic tools together to be able to understand this space of all of these 2x2 matrices. Actually, it turns out that there's just one other kind of number, a really simple thing, a simple number associated with a matrix. And if we have that, and we also have the determinant, those two numbers are actually going to be enough for us to basically understand all the behavior of all of these matrices. So there's something called the trace of a matrix. And it's very simple. The trace of a matrix is just the top left element plus the bottom right element. So the trace of this matrix is just the number A plus D. And now it turns out that if we know the trace of the matrix and also this determinant of the matrix, which we remember is AD take away BC, well, it's really remarkable that actually those two numbers, in some sense, sort of tell us up to a fairly good approximation what the behavior is of these different matrices. So basically, if you tell me the trace and the determinant, that's pretty much enough to understand the basics of what that matrix is doing in a very precise way. We're going to see this later. And so to make this more precise, we need a definition now. And this is the idea of two matrices being similar. So basically, we say that two of our matrices, M and M dash, are similar when there exists another matrix S for which this formula holds true. So what does this say? It says that if we do S times M times the inverse of S, then we get M dash. An equivalent way to say this is that S is invertible, and we have the M dash S is equal to SM. You can see that we can get this second equation here by taking this first equation and multiplying it by S on the right side of both sides of the equation, because these two are going to cancel out and give us an identity. So that's the definition of similar matrices. They're basically similar when there exists this other matrix which can kind of allow us to convert between the two things. So the way I like to think of this, basically the way I like to think of what's going on here, is that when we have this situation of similar matrices, it means that the matrix M is kind of like the matrix M dash. More precisely, if we want to do this M dash operation, then what we can do is apply the inverse of S, and then we can apply M, and then we can sort of go back by applying S. So really, in a sense, this is about converting one problem into another problem. It reminds me of a famous joke about a physicist and a mathematician on the island, and they're trying to get some coconuts. So I'm not sure if I'm telling it right, but I'm going to have a go. So basically, there's this very tall coconut tree. So basically, there's this very tall tree, and the physicist manages to get some very practical way of finding some way to climb up this tree and get the coconuts, and he takes it down. And then the mathematician has to get a coconut from a lower branch of the tree. So he also climbs up the tree and grabs the coconuts, and then he goes further up the tree and places the coconuts at the top of the tree where the physicist went. And when the physicist asks, well, why did you do that? The mathematician says, oh, I'm reducing the problem to one that we can already solve. So this is the kind of thing that we can do with similar matrices. We can get one matrix and convert it into something else, like something of the form M, and M may have a more familiar form. And so there's one more piece of sort of algebraic machinery that we're going to need to understand this whole space of all these matrices. And it's a very lovely and very powerful kind of idea. And it's the idea of using so-called eigenvectors and eigenvalues. And so basically, if we look at these eigenvectors and eigenvalues, it's going to allow us to convert these sort of more general matrices into ones that have very special kinds. And we're going to be able to find these kind of canonical special matrices that are going to be similar to the things that we're interested in. So it's a bit like these sort of classifications that they do in biology, where biologists figure out that certain animals have different species, and we can classify them. And then they have these sort of canonical examples of members of particular species, which they sort of do particular studies on. And so what is an eigenvector? Well, let's say we have one of our 2x2 matrices M. Well, it could be that we can find a certain vector. So that would be a vector like v1, v2, and it may be an eigenvector of M. So the definition is that v is going to be an eigenvector of M when v is non-zero, and when there exists a scalar, lambda, which has the feature that when we do M on our vector, so we get M of v, that results in a vector which is just lambda times the original vector. So we can write this, if we sort of expand it out, we get this equation that looks like this. So what's the idea of these eigenvectors, sort of geometrically? Well, the basic idea is when we look at these different sorts of matrices, let's look at this particular case, all right? So what this is basically doing is just stretching everything along the x-axis. And you can see that in this case, if we have a vector which is just pointing to the right, then when we apply this matrix, that vector is not going to change direction. It's just going to get stretched. So basically, these eigenvectors are these special vectors which don't actually change direction when we apply the linear map. They might be rescaled, and the scalar that they get rescaled by is called the eigenvalue of the vector. So when we find an eigenvector, there's going to be this corresponding lambda, which is going to be the eigenvalue. And basically, if we understand what the eigenvectors and eigenvalues are for a matrix, that really tells us an enormous amount about the behavior of that matrix. Okay, then, so we have this idea of eigenvectors. And remember, okay, so we have this idea of eigenvectors. And so, as I say, an eigenvector V is something which has the feature that when we do M times V, we just get some scalar times V, and that scalar is called the eigenvalue associated with the eigenvector. So using eigenvectors is a very powerful method to understand matrices. Basically, if you think about what we've done, we sort of started out with this idea that we have these kind of rectilinear coordinates that we describe everything in terms of. But actually, there's nothing about what we've done which really relied on having our coordinates as perpendicular. And so, in fact, it turns out that it's usually better to understand the matrix by having these eigenvectors as the sort of vectors that we can use to describe the kind of grid that our matrix works on. That's because these are the kind of natural directions which are special with respect to the behavior of the matrix. So anyway, how do we determine what these eigenvectors and eigenvalues are? Well, basically, this is the most important equation here, and we can rewrite it like this. We've just stuck an identity matrix in here. And so we can rearrange it to say that this should equal 0. And so what we have here is a matrix, and this matrix is multiplied by this non-zero vector, and we end up getting 0. Now, I don't want to get into too much theory, but basically this implies that the determinant of this matrix has to equal 0. And so that gives us an equation that we can solve for lambda. That's called the characteristic polynomial of our matrix. So if we just write it all out, we find this kind of form here. We want to solve this being equal to 0. So let's just write it all out. Now let's compute this determinant. This times this, take away this times this. So this is the thing that we want to equal 0. Now if we expand it out, it looks like this. And now let's recognize that there are some well-known quantities within this expression. In particular, this is going to be the trace of our matrix, and this is the determinant of our matrix. And so we can rewrite this line like this, and this is the characteristic polynomial of our matrix. So what we want to do is find the lambda that make this equal 0, and they're going to be our eigenvalues. So we can solve this. We can apply the quadratic formula, and it tells us that the eigenvalues have this kind of form. So there's going to be two different eigenvalues usually. And so we can use this kind of approach to find out what the eigenvalues are. And then for a particular eigenvalue, lambda, well, we can solve this equation to find what the eigenvector v1, v2 corresponding to it's going to be. So really what we have here is two equations. We have AV1 plus BV2 equals lambda V1, and we have CV1 plus DV2 equals lambda v2. So this is a system of equations and we can solve it. We're only going to get what the eigenvector is up to a scalar. So we're going to know the sort of proportionality between v1 and v2. But of course, anything scaled by that is also going to be an eigenvector. So, but that's fine. Any solution will do. But we just need to pick one eigenvector, then v, that satisfies these equations. And then we'll collect that together with lambda. And then we call this thing an eigenvector eigenvalue pair. So we're going to get one of those for our first lambda. But typically, you know, we're going to get two different values of lambda. So we're going to have one of these eigenvector eigenvalue pairs and another one like that. And they're sort of going to tell us all about our system. So basically, we're going to get more practice using these eigenvectors and eigenvalues. But basically, they're a very, very powerful kind of method that we can use to understand about our matrices. And what we're going to do now is do the thing I've been sort of promising throughout this video, which is to really characterize the behavior of all of these different matrices. So we're going to consider a totally general matrix now, M. So this is a general 2x2 matrix. And we have this result, which is basically classifying the sort of behavior of this matrix. Now, the way that this is working is that we're going to look at different possible characteristics that this M can have. And based on those characteristics, we're going to find a different sort of matrix, which is similar to that. So basically, these are the results that we have. We have that there are really 5 different cases that there can be. And what's governing these cases is really the nature of this kind of inequality. You know, is this a greater than sign? Is this an equal sign? Or is this a less than sign? And where does this inequality come from? Well, what we're basically doing is we're comparing this entry with this entry in this equation. So if you've solved quadratics before, you'll know that this sort of quantity here is very important. And based on whether it's positive or 0 or negative, like the whole system is going to act in a different sort of way. And so really what we're doing here is we're looking at this quantity, and that's really what's characterizing the behavior of the matrix. So it turns out then that there are 4 different cases that we need to think about. The first case is when the trace of m squared is bigger than 4 times the determinant. And in this case, basically, there's going to be 2 different special directions in space. And in this case, there's going to be 2 different special directions in space. And these are going to be these eigenvectors. These eigenvectors are going to be real things. And the system's either going to expand or contract things in those different directions. And so basically, our matrix M is going to be similar to this matrix here. And what this matrix here is doing is it's basically expanding, it's basically scaling the x coordinate by lambda, it's basically scaling the x coordinate by one of these eigenvalues, lambda 1, and it's scaling the other coordinate by the other eigenvalue, lambda 2. And so that's basically what's going on here. Okay. The next case is much more interesting. This is what's called the elliptic case. And this is characterized by this inequality that the trace of m all squared is less than the determinant of m. So if we went back to that expression before, you would see that in this case, that thing in the square root sign will actually be negative. So this is very interesting because in this case, we have complex numbers appearing. And so in this case, it turns out that our matrix is going to be similar to something of this kind of form. So I'm going to talk about how and what these expressions mean in particular later. But basically, in this case, we're going to have that alpha and beta are going to be real numbers. And so this matrix here, we could write it a different way. So we could write it like this: r cosine theta, r sine theta, r minus r sine theta, r cosine theta. So that's going to be what this special matrix looks like. So I find this really kind of mysterious and interesting because we remember this, right? These are the complex numbers that we saw before. These are the sort of matrix version of those complex numbers. And what we're seeing here is that in this elliptic case, is that basically our matrix is similar to one of these kind of complex number style matrices. And what is this doing to the plane? Well, it's doing what's sometimes called an amplitwist. Okay, so it's going to spin around all of the points on the plane, as well as like maybe amplifying them or contracting them based on whether this capital R here is greater than 1 or less than 1. So it's sort of going to amplify and twist everything around the plane, kind of like making a spiral or something. So I find this really remarkable, particularly because in a certain sense, the hyperbolic case and the elliptic case, when you analyze them directly, you can do pretty much the same analysis to begin with. But if you do that analysis, you can end up sort of finding something similar to the matrix that you can write in this kind of form. But in this elliptic case, these eigenvalues here are actually going to be complex numbers. But then you can do a further trick to get something into this kind of form. So you can really kind of get rid of the complex numbers. But I sort of think it's interesting philosophically that even when you're working with these real matrices, there's sort of complex numbers are knocking on the door and asking to be invited in some sense. In fact, we saw similar things with hyperbolic geometry, with the complex lines and points in projective geometry. Anyway, let's continue with our cases. The next case is a very simple one. So this is where the trace of our matrix squared is 4 times the determinant. So that's when that expression in that square root for the eigenvalue lambda is equal to 0. Okay, so in this case, there's actually only going to be one solution to that equation. And there's sort of, there's a sort of simple case of the parabolic thing, and there's a complicated case. This is the simple case. This is the case where our matrix is just something times the identity matrix. So it already has this kind of special form here, but with lambda 1 equal to lambda 2. And so in this case, we're sort of already done, and it's a kind of simple case. The final case to deal with is this one. It's called the parabolic non-diagonal case. So this is where we have a similar relationship between the trace and the determinant, but in this case, our matrix is not diagonal. And it turns out in this case that our matrix is similar to a matrix like this. So, okay, what I'm going to do now then is I'm going to go through those different cases in a little bit more detail. I just want to give you all of the kind of details that you need to apply the recipes. I'm not really going to argue very much about the logic behind what's going on. And I'm actually going to put some links to some papers which are really good, which explain about what's actually going on here. Essentially, we're basically applying what's called Jordann form, where we're translating these matrices into Jordann form. But let's have a look at this in more detail. So firstly, this hyperbolic case then. So we get, from solving our equations, we get these 2 different values of lambda. And because we're assuming that this is positive, we know that these 2 different eigenvalues here, lambda 1 and lambda 2, are going to be real. And so we have these 2 different eigenvector eigenvalue pairs, u lambda 1 and v lambda 2. And we can obtain u basically by finding a solution to this equation. Basically, to save you work, this is something that we can use as a value for this eigenvector u. We can have it as the vector minus b a take away lambda 1. And we can do similar for the eigenvector v associated with lambda 2. It has this kind of form. So then once we have those eigenvectors, we're going to put them together, and that's going to form this matrix S. Now, it turns out that this matrix S has a non-zero determinant. It can be inverted. And so we actually have this equation here. And you can check this if you, and you can check this. To check this, you can work out that M of S is equal to S times this diagonal matrix here. So I've just given a recipe for trying to understand the behavior of these so-called hyperbolic matrices. And let's actually apply it to this case here with this matrix. So here I've written the matrix, and the first thing we want to do is to check that it is hyperbolic. So we're going to calculate the trace and the determinants, and then we can see that this inequality is holding. So we know it's one of the hyperbolic case. Now, we have this formula here for the eigenvalues, and if we compute this, we find that the eigenvalues here are 2 and minus 3. So we just get those out of this expression here. So the next thing to do is to calculate the eigenvectors associated with those things. So u is the eigenvector associated with lambda 1, and we have this expression for it here. So applying this, we get that this is one of the eigenvectors. It's minus 1, minus 1. So if we're correct here, then it should be the case that if we have a look at this vector, minus 1, minus 1, then we should see that something that's going in that direction, when we apply this linear map, the image should also be going in the same direction. In fact, it should be going in that direction twice as far, because lambda 1 equals 2. That's our scaling factor. So let's have a look if this is true. So we could have a look on here. This is a wonderful app, by the way. I should say this was written by Steve Phelps. I'll put a link to this app in the description of the video. You can go on this and you can explore all this matrix geometry for yourself. But we're going to look at a different app this time, which is this one here. So basically, if I move things a bit, yes, you can see that the matrix here is given at the top right, and we can vary the entries of the matrix by moving these sliders. And then we can look at what happens to a particular vector under this map. And indeed, if we pick minus 1, minus 1, then we see that the image of that, this C dash here, is in the same direction, but it's twice as far, which is what we'd expect. Indeed, you can see that any kind of, any multiple of that vector minus 1 is also going to be an eigenvector, but we'll pick minus 1 because it falls out naturally from our formula. So far so good. Now let's get the other eigenvector, the one associated with the eigenvalue lambda 2 equals negative 3. And we find that that's the eigenvector minus 1, 4. So if we have a look now at this vector minus 1, 4, maybe it's not so easy to see, but I think its image is lying on that straight line. So if we draw a straight line through C in the origin, we'll have to zoom out a bit. yes, we see that the image does indeed line up. Now it's going in the opposite direction this time, and that's because our eigenvalue is -3. So we have a look at that vector, -1, 4, and then we have to times that vector by -3. So swap its direction and make it 3 times longer, and we find where the image is. But hopefully you can see the essence of what's going on here. And then what we do next basically is we want to form this matrix S that we can use to demonstrate that that our original matrix M is similar to this diagonal matrix. So this matrix S is just formed by concatenating these eigenvectors here, and then we can check that this expression does indeed hold. So we invert this matrix S. So this is our general recipe for inverting a matrix. And when we apply this to S, we get this matrix here. And so if we've done everything correctly, it should be the case that this equation should hold. And indeed, that is the case. So I'll just show you the math here. You can check it at your own leisure. So what this is basically telling us then is that our matrix is basically similar to this matrix here. And so basically this is what it would look like if instead of using our original kind of XY coordinates, we used coordinates which are based on using the eigenvectors of this matrix, the sort of natural coordinate system. You can see what this matrix is doing now. It's basically just sort of warping things along the X and the Y axis, but it's just sort of, well, okay, it's flipping things round in the Y axis, and it's making things 3 times taller, and it's making things twice as wide. So that basically is how we deal with this hyperbolic case. Now, what about the elliptic case? This is, you know, in a sense, it's more complicated, but in another sense, it's kind of similar. So basically, in this case, we've got the trace of M all squared is less than 4 times the determinant of M. And so in this case, let's pick alpha to be half of the trace of our matrix. And then we can notice that we can rewrite this as -1 times this positive quantity here. And actually, if we define beta to be this is going to be a real number. And we can say that our eigenvalue here is going to be, well, there's going to be 2 eigenvalues. There's going to be lambda1 is equal to alpha plus beta I, and there's going to be lambda2 is equal to alpha take away beta I. So I here is the square root of -1, and beta is this quantity here, and alpha is this quantity here. And so basically at this point, we can just apply the same kind of reasoning as we did before. And we can then say, okay, I'll just use exactly the same reasoning as in the hyperbolic case. And I know that my matrix M is going to be similar to this diagonal matrix here. But hang on, this is a bit strange because we know now that our eigenvalue, lambda1, is complex. So is lambda2. So, okay, we've shown that our matrix is similar to this complex matrix, but that's a bit like, where did these complex numbers come from? Who ordered those? So it would be nice if there was another step where we can then relate this matrix to something a bit more familiar. And so let's do a bit more reasoning. Let's now consider this matrix here. And you might remember this kind of form. This is the form of a sort of complex number as a matrix. And now it turns out, okay, I've corrected this. And so it turns out that if we define H to be this matrix here, then we have that this sort of, complex number representative matrix, which is actually a real matrix, paradoxically enough, that this is similar to this matrix full of eigenvalues. This one here that we got, but we didn't really like it because it had like complex stuff in it. And so now we can do a bit of manipulation, right? If we get this expression and we multiply it by h on the right and h to the minus 1 on the left, we get this. And then we also have our original expression for m. And so if we take this and we stick an s on the left and an s on to the minus 1 on the right, we can do similar here. And so we find that this m here is the same as this, which is the same as this, which is here. And then with a little bit of manipulation, we see that what we've really shown is that our original matrix is similar to this matrix here, this one that looks like one of these complex numbers. So this is really remarkable. Because we've basically shown that in this elliptic case, our matrix is similar to one of these kind of amplitwist matrices. So this really helps us to gain a kind of intuitive understanding of what these elliptic matrices are doing. Okay, then. So now let's have a look at this. Okay, so now let's have a look at one of these elliptical examples. So this is, in a sense, much more interesting because we get this kind of mysterious connection here with the complex numbers. So you can see that in this case, our letter F is getting a bit sort of rotated, and we're going to get some much deeper understanding of what's really going on here. So we're just going to apply the methods that I've just talked about. There's quite a lot of calculation here, so I'm going to go quite quickly. I urge you to, pause the video, work this out for yourself and check. And I also give some links to some great resources that you can understand more of the sort of reasoning about why these kind of things that are happening. But let's just see the computation. So here's our matrix. We work out the determinant and the trace, and then we can see that this inequality is holding, so we know we're in the elliptic case. We have this formula here for the eigenvalues. Computing them, we find that now the eigenvalues are 1 plus I and 1 minus I. So complex eigenvalues, what does that mean? We have these formulas here, which are telling us about the eigenvectors. And so we can work out what the eigenvector is associated with 1 plus I, and it has components 1, 1 minus I, and here's the eigenvector associated with 1 minus I. It has components 1, 1 plus I. So we've worked out the eigenvectors. They are again complex. So this kind of intuition that these eigenvectors are these sorts of directions in space, through which the thing is only going to expand or contract, that's a little bit debatable now, right? Does that intuition still make sense? Well, perhaps not exactly, because now we're really dealing with something which is involving rotation. And if you've studied my projective geometry series a lot, you'll know that sometimes you get these sort of imaginary numbers coming in when you have things that are rotating as opposed to being translated. There's some very deep connection here. So anyway, we'll continue to apply the recipe that we talked about before. So we're going to concatenate these eigenvectors here and form this matrix. And now step one, we want to sort of show that we have that our original matrix is similar to this diagonalized one. And so if we take this expression, I'm putting a question mark here because this is an equation that we want to check. And if we multiply both sides of this by s on the right, we get this equation that we can check. And indeed, if we just compute this out, we get that the left side is this, and the right side is the same. So That's good. Okay, so we've done the sort of first step. Now the second step is we actually want to make contact with a matrix which is completely real, and it's one of these sort of rotation matrices. So we recall that we can write our lambda, our eigenvalue here as alpha plus beta I, and in this case, alpha and beta are both 1. And our second eigenvalue is alpha take away beta I. And so this matrix A, this is going to be the rotation matrix that we want to eventually show that M is similar to. So what we're going to do is we're going to do this in steps. We're going to start by showing that A here is similar to this diagonal matrix here. So to demonstrate that, we cook up this matrix H, which I've prescribed should have this kind of form in general. So if we just work it out in this case, it looks like this. And then we hope that A is similar to our diagonal matrix. And again, we can multiply both sides of this by H on the right. So we want to check that this equation is holding true. And indeed, A is this, and Ha is the same. And indeed, AH is this, and H times our diagonal matrix is the same thing. So that equation holds true. And so now we're basically done. We know what H is, and then actually to sort of finish the job, and so actually to finish the job, what we want to do is to sort of put those two steps together. So we want to show that M here is similar to this rotation matrix here. So what we want to do is we want to be multiplying by this and so what we want to do is we want to show that M is equal to Q times this rotation matrix times the inverse of Q. So we need to work out what Q is. I'm defining Q as S times the inverse of H. So we need to invert this matrix H here. And so we do that. Here it is. Okay, this is the same matrix simplified a bit. And then we just want to check that this equation is true. Well, let's work out what Q is. So Q is S times the inverse of H. We work it out to be this. And that's nice because Q is a real matrix, right? Which is important. So just to finish this, we just want to check that this equation is true. Well, we do the same thing we've done before. We multiply both sides on the right by Q. We want to check that this equation is true. And indeed, MQ is the same as Q times our rotation matrix. Whew, so we're done. So, okay, what can we conclude from this? Well, what we can conclude is that our original matrix is going to be similar to this matrix here. So let's have a look at this matrix here. It's got these sort of column vectors, 1, -1, and 1, 1. So let's have a look at those. So this one should go to 1, -1. And this one should go to 1, 1. And you can see that what this matrix is doing is it's just rotating. And you can see that what this matrix is doing is one of these sort of amplitwist motions. And then there's just a couple more cases to deal with. There's the parabolic diagonal case. Well, that's just, we just have a multiple of the identity matrix to begin with. There's nothing to do. And then finally, there's this other kind of parabolic non-diagonal case. So this is a bit weird. I'm not going to justify too much here. I'll put a link to a paper that explains what to do really well in this case. But basically, if we go back to our equation, which told us what our eigenvalues are, we find that there's just this eigenvalue, which is half of the trace of our matrix. So now let's form this matrix M. And it's just going to be our original matrix, take away lambda times the identity. So it has columns like this. Like, let's imagine this is the form of M. And in fact, you can prove that one of these column vectors at least has to be non-zero. So we can look at two different cases, right? Let's look at the case where this second column vector is non-zero. In that case, we write S like this. The alternative is that our first column vector is non-zero, and then we can write S like this. In either case, basically, we then have this equation holding. So this kind of completes the job. We've found these sorts of canonical forms for our different. We found these different sorts of canonical forms for our different matrices. So, okay, let's do an example then in this parabolic case. So we're going to take a look at this matrix here. And then if we calculate out, we find out that the determinant of this thing is 16 and the trace is -8. And so these are both equal to 64. So yes, we do have this parabolic case, and clearly this is not one of these multiples of the identity matrix. So we can carry on, just apply the recipe. So we calculate that we find this eigenvalue just by using our equation. Note that the thing in the square root of the equation is 0 now. So that equation just gives one answer, one eigenvalue, which is -4. So now we just continue following the recipe. So we work out what this matrix N is, which is going to be M take away the identity matrix times lambda. So it's going to be this. And then basically we want to just make sure that, and so we have this kind of situation. And the recipe I was saying before is basically that we know that at least one of these two columns here is going to be non-zero. And we just have to pick, something for that case. So, if y1, y2 is not 0, then we can define our matrix S like this. If this is non-zero, then we can define our matrix S like this. If both of them are non-zero, then we can take our pick. So we have different choices about how to cook up this similar matrix. So we have different choices about how we can cook up this matrix S that we use for similarity. So in my case here, I've got that, I know for sure that the first column is not 0. So that's obviously not 0, 0. So I can define my matrix S like this. And then basically to finish the job, I just have to check that this equation is true. Well, I do the usual thing, multiply it on both sides by S. So I want to check that this is true. And so MS is this, and S times this upper triangular matrix is the same thing. So we're done. So basically what I've said allows you to understand all of these 2x2 matrices. And you'll notice, if you think about it for a while, that really what's determining the behavior of these matrices is just the value of the trace of the matrix and also the determinant of the matrix. And so, you could write down, and so, you could look at those four cases and write down some inequalities, which will tell you how this sort of four-dimensional space of all matrices gets divided up. And you can also do other things, like you can analyze what happens in these different cases. For example, when the determinant is 0, when the determinant is 1, and so on. Okay, so I want to finish by talking about a case that I find really, really geometrically pleasing. And that's the case where we want to understand the behavior of this special linear group, SL2. So remember, this is the group of invertible matrices that have a determinant equal to 1. And so it turns out that this is a very kind of special family of matrices that has a really lovely way of thinking about it geometrically. So basically, in this case, there are going to be these three really important subgroups. This one, which we call K, which is basically SO2, or we could think of it as the circle group. And so we've already seen this subgroup before. Here's another one. This is called A. And this basically consists of the kind of hyperbolic matrices. And then this one here, N, this consists of the parabolic matrices. So here with A, you can see that we're looking at these different matrices and they're sort of parameterized by this positive number R here, whereas N here is parameterized by this real number X. Okay, so here comes the amazing theorem. This is called the KAN decomposition theorem. And I'll put a paper about this, a link to in the description of the video. But this is really beautiful. Basically what we're saying here, this is our theorem, is that for every member of SL2 of R, we can write that member uniquely as a matrix K, which comes from this scripty K subgroup, times a matrix A from scripty A, times a matrix N from scripty N. Okay, maybe I'll underline this so it doesn't get confused with the natural numbers. But yeah, this is a really remarkable result. Basically, it's saying that if you take any matrix in SL of 2, then that matrix can be expressed as some member of this subgroup times some member of this subgroup times some member of this subgroup. So really, what it's saying is that all of the kind of matrices in SL2 of R, they all basically have this kind of form, that they can be written as a product of three different matrices like this. So in a sense, what we can really do is parameterize SL2 just by varying this angle theta and this positive number R and this real number X. Okay, so a really beautiful thing about this KAN decomposition is that it gives us a way to visualize this special linear group SL2R. And it's actually a three-dimensional space, right? So what our theorem's basically telling us is that we can write any of the matrices in SL2R, any of these 2x2 matrices that has a determinant of 1, well, we can write it in this kind of form here. And here, theta is going to be something between 0 and 2 pi. R is going to be a positive number, and X is going to be a real number. And so if you think about it, what we really have here, if you imagine varying these different parameters here, theta, R, and X, then the thetas, the different parameters are going to form a circle, and these different R parameters are going to form this sort of interval of positive real numbers, and then the X values are going to form the real line. And so we can really think that if we times together all of these different manifolds, we're going to get a sort of manifold which in some sense looks like SL2. And so there's various ways that you can think about this. A topologist would probably say, okay, this is isomorphic to, a topologist would probably say, okay, this is isomorphic to an open interval. This is isomorphic to an open interval. These two times together are isomorphic to the interior of a two-dimensional disk. So we have a two-dimensional disk times a circle, and that means that what we basically have is like the interior of a torus shape. So basically, SL2 looks like the inside of a donut. I suppose this is the way a topologist would think about it. But I think there's actually a slightly more natural way to think about the geometry of SL2, and that is basically to say that okay, what one of these points in SL2 is really described by a sort of angle, and then an amount r, which we're coming out of this circle. So if you imagine we have this sort of, and then x, which is sort of elongating this circle into a cylinder. So if you imagine what we have here is a plane, then when we have a certain angle, that's going to be a certain angle around this unit circle. And then when we have our value little r, then we're going to come out away from the circle a distance r, and then we're going to go up by a distance x. And that's going to give us a point in this 3D space, perhaps here, for example. And we can really think of this as the point where this matrix Q theta R X sort of lives in some sense. And so if you want to be a bit more precise here, what we want to do is put Q theta R X at these coordinates here. So notice that we're basically looking at all of three-dimensional space, except this sort of unit cylinder here. So we're really looking at the sort of complement of the unit cylinder. And this is what I claim is basically how we should think about SL2. And then we know from before that basically, if we look at the trace and the determinants of these matrices, that really tells us all of the sort of qualitative information about the behavior that's going on. And in fact, we know that the determinant's always 1 for these matrices. And so, this is where we should put this Q theta Rx. And then what we could do is draw these different sorts of regions. So remember, remember by checking these sort of inequalities, we can see whether our matrix is going to be hyperbolic or parabolic or elliptic. And so we can basically draw the regions corresponding to these things, and these are going to correspond to these sort of regions of this 3D space. And basically looking at those regions is going to tell us about the behavior of our matrix.